Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with rogue stars, the loneliest travelers of the galactic halo. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried and nice atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Rogue stars are celestial bodies that have been ejected from their initial star system, drifting through the cosmic expanse without a defined orbit around any galaxy. This phenomenon occurs due to gravitational interactions, often involving dense stellar clusters or the remnants of supernovae. Such stars possess a unique allure, embodying the essence of solitude in the universe as they traverse the void, untethered by the gravitational embrace of their former companions. In the galactic halo, these solitary travelers frequently exhibit high velocities, propelled into interstellar space. The velocity can reach several hundred kilometers per second, enabling them to cover vast distances across the cosmos. Their origins are often traced back to crowded regions where stellar interactions are commonplace, leading to an occasional cataclysmic event that results in their expulsion. Rogue stars contribute to our understanding of galaxy formation and evolution, as their movements provide insight into the dynamics of star clusters and the gravitational forces at play. Observations of these entities reveal a diverse population, ranging from massive, luminous giants to smaller, dimmer objects. Their isolation offers a unique opportunity for studying the chemical composition of the universe, as many of these stars retain the elemental signatures from their birthplaces, enriching our knowledge of cosmic history and the life cycle of matter. The discovery of rogue stars marked a significant milestone in astronomical research. Initially, the concept emerged in the early 20th century when evidence began to surface regarding stars that did not adhere to the gravitational confines of their respective galaxies. Observations of peculiar trajectories, often deviating from expected orbits, hinted at their unconventional paths. This led to a gradual understanding that some stars, propelled by gravitational interactions or cataclysmic events, could traverse vast interstellar distances. The emergence of sophisticated observational technologies, such as large telescopes and spectroscopic analysis, further enhanced the study of these celestial nomads. Astronomers identified instances of hypervelocity stars, which traveled at astonishing velocities, indicating a violent origin, possibly from interactions with supermassive black holes at the centers of galaxies. The detection of these stars spurred inquiries into their formation mechanisms and the processes that facilitated their ejection from galactic halos. As research continued, the realization dawned that rogue stars contribute to the galactic ecosystem in profound ways. They carry with them primordial elements, remnants of ancient nucleosynthesis, providing insights into the formation of galaxies and the expansion of the universe. The ongoing quest to catalog and analyze rogue stars is reshaping our understanding of stellar evolution and the dynamics of the cosmos, revealing the intricate interconnectedness of celestial phenomena over vast stretches of time and space. Formation mechanisms of rogue stars arise from a variety of processes. Gravitational interactions within star clusters often lead to the ejection of individual stars. This dynamic occurs when close encounters between massive bodies disrupt the orbits of nearby stars, sending them careening into the expansive halo of the galaxy. The energy of these interactions is immense, creating pathways for stars to escape the gravitational grip of their birth clusters. Another route to rogue star formation involves the violent aftermath of supernova events. When a massive star reaches the end of its life cycle, explosive ejection can propel nearby companions into interstellar space. Such forces can impart sufficient velocity to render these stars independent, removing them from their original stellar neighborhoods. In some instances, the merger of binary star systems produces rogue stars. When two stars collide, the resulting single entity can possess enough momentum to break free from gravitational bonds. This process, often chaotic, leads to the birth of new stellar entities that embark on solitary journeys through the vastness of space. These mechanisms highlight the complexity of stellar life cycles. Each rogue star carries a unique history, a silent testament to the turbulent forces at play within the galaxy. Their solitary paths contribute to an ongoing narrative of cosmic evolution, reflecting the ever-changing nature of the universe. The force of supernovae plays a pivotal role in the ejection of stars from their original positions within galactic structures. Upon the explosive death of a massive star, a shock wave radiates outward, displacing surrounding gas and dust. This violent release of energy can impart sufficient velocity to nearby stars, propelling them into the vastness of the galactic halo. In these regions, the remnants of supernova eruptions mingle with interstellar material, creating environments ripe for star formation. Yet, for those that escape the gravitational embrace of their parent galaxy, their journeys mark them as wanderers. These ejected stars, now free, traverse the cosmos, often isolated from the clusters and constellations they once belonged to. The remnants of these colossal explosions can also trigger the formation of new stars in their wake. As the material from a supernova cools and collapses under its own gravity, it may give birth to a new generation of celestial bodies. While some stars embark on solitary paths, others may eventually find companions among the remnants of their explosive origins, creating new dynamics within their respective environments. In this quiet aftermath of destruction, the cycle of life and death within the universe is laid bare, revealing the intricate connections between events that appear so chaotic and the serene embrace of the cosmic void. Gravitational interactions among celestial bodies shape the dynamics of these stellar encounters, influencing trajectories and modifying orbits. The subtle pull of gravity governs the behavior of rogue stars, causing them to interact with nearby objects in profound ways. These encounters can result in the exchange of energy and momentum, prompting stars to alter their paths or even be captured by the gravitational influence of more massive bodies. When a rogue star passes near a cluster of stars, tidal forces may induce disturbances within the cluster. This can lead to a phenomenon known as stellar scattering, where the rogue disrupts the balance of gravitational forces and sends other stars careening into newly established trajectories. The resulting chaos can lead to the formation of new binaries or the ejection of stars into the interstellar medium. Thistropes quarks can lead to the formation of new binaries or the ejection of stars into the interstellar medium. The aftermath of such encounters often leaves behind remnants of their interactions. Stellar debris and clusters of gas may mark the sites of these gravitational duels, creating a celestial landscape dotted with the vestiges of past collisions. Each encounter carries the potential for new formations as remnants of old stars merge or collide, giving rise to fresh stellar bodies. Through these dynamic interactions, the universe continuously reshapes itself, illustrating an intricate web of relationships that persists in the vastness of space. The galactic halo, an expansive and diffuse region surrounding the primary disk of a galaxy, serves as a repository for ancient stellar remnants and dark matter. This region is characterized by its sparse density, yet it houses a significant amount of the galaxy's mass. Composed predominantly of old stars, globular clusters, and a substantial amount of non-luminous dark matter, it reveals the remnants of formative processes that transpired billions of years ago. Within this halo, stars drift along elongated orbits, often far removed from the gravitational influence of the galactic center. The distribution of these celestial bodies follows a roughly spherical shape, with stars found at various distances from the core, contributing to the overall gravitational balance. Dark matter, invisible and enigmatic, comprises the majority of this structure, influencing the motion of visible matter and playing a crucial role in the galaxy's formation and evolution. The composition of the galactic halo also includes a variety of chemical elements, primarily those forged in earlier stellar generation. This region acts as a bridge between the galaxies and their surrounding cosmic environment, highlighting the ongoing interactions between different components of the universe. Such interactions not only shape the halo, but also provide insight into the history and dynamics of the galaxy as a whole. The process begins in vast molecular clouds, dense regions where gravity pulls together gas and dust. Over millions of years, these materials coalesce to form protostars, characterized by immense heat and pressure at their cores. As nuclear fusion ignites, these young stars enter the main sequence phase, steadily fusing hydrogen into helium, illuminating the surrounding region with their radiant energy. Eventually, the life cycle progresses toward the star's death. The fate of a star largely depends on its initial mass. Smaller stars, like our Sun, will eventually expand into red giants, shedding their outer layers and leaving behind a dense core known as a white dwarf. In contrast, more massive stars undergo a more violent end, exploding in supernovae, dispersing heavy elements into the surrounding space, enriching the interstellar medium. Through these cycles, remnants of stellar life contribute to the formation of new stars and planetary systems. Occasionally, gravitational perturbations or interactions within dense clusters can lead to stars being ejected from their home systems. These rogue stars drift through the galactic halo, solitary and wandering, carrying with them the history of their origins. Their paths provide crucial information about the gravitational influences and interactions that dominate their galactic environment, revealing the complex web of cosmic evolution. Types of rogue stars vary significantly, each classified based on their mass, luminosity, and formation history. Among them, one can find low-mass stars, often red dwarfs, which quietly drift through the vast expanse. These diminutive giants are the most abundant in the universe, exhibiting long lifespans that can extend to trillions of years. Their faint glow renders them nearly invisible to the naked eye, yet they play a crucial role in the galactic ecosystem. More massive rogue stars, classified as blue or yellow supergiants, stand out in their brilliance. They are born in energetic environments, giving rise to explosive events such as supernovae when their life cycles culminate. This explosive end contributes to the chemical enrichment of the surrounding space, seeding new generations of stars and planetary systems. The dynamics of these solitary wanderers extend to their interaction with dark matter and gas clouds within the halo. Some may capture interstellar material, while others become part of gravitational encounters with other celestial bodies. Their solitary existence offers insight into the conditions that lead to star ejection processes, unveiling the mechanisms behind their departure from established stellar clusters. Understanding these classifications and characteristics allows for a deeper grasp of the forces governing the cosmos and the intricate evolution of galaxies. The trajectories of unbound stars take them on journeys through the vast interstellar medium, often resulting in paths that lead to regions of space far removed from their original galactic homes. Over time, these stars become increasingly isolated, drifting away from the gravitational influence of their parent galaxies. The absence of a stable gravitational anchor results in an array of potential fates, each determined by the dynamics of their individual encounters with other celestial bodies. Some may pass through dense stellar clusters, where gravitational interactions can alter their courses significantly. Others might find themselves drawn into the gravitational wells of massive objects, such as black holes or neutron stars, resulting in dramatic changes in velocity and trajectory. This interplay illustrates the chaotic nature of the cosmos, where even the loneliest travelers can encounter unforeseen circumstances. Over billions of years, many of these unbound stars are fated to become part of the cosmic background, shining faintly in the depths of space. Their light stretching across vast distances, they contribute to the diffuse light of the universe, remnants of once vibrant stellar communities. Rogue stars, drifting through the galactic halo, differ fundamentally from their bound counterparts. These solitary wanderers have been ejected from their original stellar systems, often resulting from gravitational interactions or catastrophic events such as supernova explosions. This expulsion leaves them untethered, traversing vast cosmic distances without the gravitational embrace of nearby stars. The dynamics of these stars contrast sharply with those of bound stars, which remain anchored within well-defined orbits around a galactic center or associated stellar clusters. Bound stars, by nature, interact within gravitational fields, forming intricate systems where they can share mass and energy. This interaction fosters a rich environment for the formation of planets and other celestial bodies. In contrast, rogue stars exist in isolation, a testament to the unpredictable nature of stellar evolution. Their paths can take them through regions of space devoid of significant mass concentration, resulting in extended periods of solitude. The luminosity and composition of rogue stars can provide insights into their origins and the conditions of their birth. These solitary entities may exhibit different spectral characteristics compared to their bound siblings, revealing varied histories of nuclear fusion and elemental formation. As they traverse the universe, rogue stars serve as markers of cosmic events, their presence silently narrating the story of stellar evolution and the dynamic interplay of gravitational forces across the cosmos. Detection of rogue stars relies on a variety of advanced observational techniques. Telescopes equipped with sensitive instruments capture faint light signatures emitted by these isolated entities. Spectroscopy enables astronomers to analyze the light, revealing chemical compositions and velocities, which can indicate the star's origin and trajectory. Wide-field surveys enhance the search for these elusive objects by mapping vast regions of the sky. Utilizing the light from surrounding stars, researchers identify anomalies that suggest the presence of a rogue star. These efforts often employ large apertures and advanced imaging technology to discern these faint wanderers against the backdrop of the cosmos. Gravitational lensing also plays a pivotal role in detection. When a rogue star passes in front of a more distant light source, its gravitational field bends the light, creating observable distortions. Such events can provide critical data regarding the mass and distance of the rogue star, enriching our understanding of these celestial nomads. The study of these stars is complemented by simulations and modeling, which predict their behaviors based on known physical laws. By combining observational data with theoretical frameworks, scientists gain insights into the origins of rogue stars, their interactions, and their eventual fates. Each discovery adds a layer to the existing knowledge of the galactic halo, revealing the complexities of stellar migration in a vast and ever-evolving universe. The complexities of stellar migration are further influenced by the presence of dark matter, an unseen component that permeates the universe. This enigmatic substance constitutes approximately 27% of the total mass energy content, shaping gravitational interactions between visible matter, rogue stars, unbound by the gravitational influence of their original systems, traverse the galactic halo, propelled by the gravitational forces exerted by dark matter. These celestial wanderers often find themselves in regions where dark matter density fluctuates, which can significantly affect their trajectories. The gravitational pull of dark matter halos can alter the paths of rogue stars, redirecting them into new territories. As they travel through these vast expanses, their velocities are influenced by the density and distribution of this elusive matter, creating a dynamic interplay between the stars and their invisible surroundings. Observations reveal that rogue stars can travel at remarkable speeds, often exceeding several hundred kilometers per second. This velocity allows them to escape the gravitational grasp of their host galaxies, becoming solitary entities within the cosmic void. The presence of dark matter not only facilitates their ejection, but also dictates their ultimate fate as they journey through the galaxy. Understanding the role of dark matter in rogue star movement is essential for unraveling the intricate web of cosmic interactions that shape the universe's structure and evolution. Rogue stars play a pivotal role in the ongoing evolution of the galaxy, influencing both their immediate environment and the broader cosmic framework. These solitary wanderers contribute to the feedback loop of galactic dynamics by participating in processes that can alter star formation rates and the distribution of matter within various galactic regions. When a rogue star passes through a dense molecular cloud, it can trigger the collapse of that cloud, leading to the birth of new stars. This interaction illustrates a delicate balance, as newly formed stars may themselves eventually become rogue candidates, continuing the cycle. In regions where rogue stars proliferate, their presence can lead to the disruption of established stellar populations. The gravitational influence they exert on surrounding matter can create zones of instability, affecting the orbits of other stars and potentially resulting in further ejections. Over time, this activity shapes the galactic halo, the vast, diffuse region that envelops the galaxy, populated by these nomadic celestial bodies. The ejected stars, moving away from their origin, contribute to the enrichment of interstellar space with heavier elements, a process critical for the formation of planets and the emergence of life. Kinematic studies reveal that rogue stars exhibit a diverse range of velocities, influenced by their initial ejection mechanisms and subsequent gravitational interactions. These velocities can vary significantly, spanning from a few kilometers per second to more than 200 kilometers per second. The distribution of these velocities provides insight into the dynamics of stellar ejection. High-velocity stars often originate from violent encounters in dense stellar environments, such as globular clusters or the vicinity of supermassive black holes. In contrast, lower-velocity stars may result from more gentle slingshot processes, where gravitational interactions gradually propel them away from their birthplaces. This variation is not random. It follows a specific statistical distribution, The characteristics of these distributions allow astronomers to trace the origins of rogue stars and understand the gravitational forces at play within their parent structures. Such studies highlight the importance of rogue stars in the broader context of the galaxy's evolution. Their trajectories can influence the orbits of other stars and contribute to the overall mass distribution in the galactic halo over eons. These solitary wanderers interact with interstellar matter, gradually altering their surroundings and playing a pivotal role in the cosmic life cycle. Each rogue star, with its unique velocity profile, becomes a solitary witness to the ever-changing landscape of the universe. Galactic events exert a profound influence on these solitary travelers, shaping their trajectories and illuminating their paths. Interactions with massive structures, such as stellar clusters or the gravitational pull of black holes, can alter the course of a rogue star's journey as they traverse vast distances. The remnants of supernova explosions can create turbulent regions in the interstellar medium, affecting the density and composition of the gas and dust surrounding them. The remnants of ancient galaxies hold clues to their origins, revealing a history marked by collisions and mergers. These encounters can impart kinetic energy to rogue stars, propelling them into the outer reaches of the galactic halo. Over millions of years, these interactions contribute to a complex web of gravitational forces that dictate the movement of these stars. In regions where star formation is rampant, rogue stars may encounter dense clusters, leading to dynamic interactions that can change their velocities significantly. The impact of these events is not limited to immediate physical alterations. They also influence the chemical compositions of the stars, enriching them with elements produced in stellar processes. Observing these wandering entities provides insights into the conditions present in the early universe, illustrating the consequences of gravitational dynamics and stellar evolution across cosmic timescales. They serve as markers of galactic history, revealing the intricate dance of matter and energy in the cosmos. Galactic studies of famous rogue stars provide insight into their unique journeys through the universe. One notable example, Uiscatio 14, exhibits an extraordinary velocity, traveling at speeds exceeding 180 kilometers per second. This remarkable pace suggests it has been ejected from its parent star cluster, propelled by gravitational interactions. The study of this star reveals the forces at play within its origin, contributing to the understanding of stellar dynamics and the environments from which they emerge. Another intriguing case, BPM 150, represents a different aspect of rogue star behavior, located approximately 100,000 light-years from its initial birthplace. It offers a glimpse into the processes that disrupt star systems. The ejection mechanisms of BPM 150 highlight the complexities of gravitational encounters, particularly in crowded stellar environments. In the context of the galactic halo, these stars offer valuable data on the distribution of mass and dark matter. Their trajectories, influenced by gravitational interactions, aid in mapping the halo's extent and density. The peculiar paths taken by these celestial wanderers disrupt the traditional understanding of stellar formation, illustrating the dynamic nature of galaxies. Each rogue star serves not only as a solitary beacon, but also as a narrative thread in the broader story of cosmic evolution. Stellar populations within the galactic halo reveal significant insights into the formation and evolution of galaxies. These rogue stars, often ejected from their stellar nurseries, contribute to a unique demographic distinct from their more stable counterparts within the galactic disk. Containing primarily older stars, this region harbors remnants of the early universe, reflecting the conditions of its formation. The dynamics of these populations are influenced by gravitational interactions, often resulting in ejections due to close encounters with massive bodies. This process leads to the isolation of rogue stars, which drift through the vast emptiness of the galactic halo. Their composition provides clues to the primordial matter that preceded the formation of galaxies, enriching our understanding of elemental abundance and chemical evolution. Studying these solitary entities reveals the mechanisms governing their trajectories. It becomes evident that the gravitational influence from surrounding structures can alter their paths, sometimes sending them into intergalactic space. These interactions not only dictate individual fates, but also inform the history of star formation processes across cosmic time. Observations indicate that the population of rogue stars is more extensive than previously thought, challenging assumptions about the density and distribution of matter in the universe. This newfound understanding reshapes the framework within which stellar evolution is studied, inviting further exploration into the nature of these celestial wanderers. Metallicity, the abundance of elements heavier than helium, plays a crucial role in distinguishing the various populations of rogue stars. This characteristic offers insight into their origins and evolutionary pathways. Low metallicity suggests an early formation in the universe, often linked to the primordial gas from which they emerged. In contrast, higher metallicity indicates a more recent birth, typically influenced by the enriching processes of supernovae and stellar winds. And age is another determining factor, presenting a spectrum of existence among these celestial nomads. Some rogue stars may be remnants of ancient stellar populations, older than 10 billion years, while others are relatively young, formed in the wake of dynamic cosmic events. This diversity implies differing histories of interaction and isolation, contributing to their current trajectories through the galactic halo. The vastness of this region, filled with low-density gas and dark matter, provides an expansive canvas for the exploration of these stars. Their paths can reveal the gravitational influences of nearby galaxies and the effects of gravitational scattering. By studying their metallicity and age, researchers can piece together the narrative of a galaxy's evolution, shedding light on the interplay of stellar life cycles and the galaxy's larger structural framework. Each rogue star, in its solitary journey, contributes to the understanding of cosmic history. The interstellar medium, a vast expanse of gas and dust, is shaped significantly by the influence of rogue stars. When these solitary travelers traverse the galaxy, they interact with their surroundings, imparting energy and momentum to the particles within this region. The passage of a rogue star can create shock waves, compressing nearby clouds of gas and triggering the formation of new stars in the process. This interaction leads to a dynamic environment where elements are redistributed and the chemical composition of the medium is altered. The energy released during the life cycle of a rogue star, particularly during supernova events, enriches the interstellar medium with heavy elements. These elements play a crucial role in the formation of future stars and planetary systems. Rogue stars also contribute to the heating of the interstellar medium. Their radiation can elevate the temperature of surrounding gas, impacting the thermal balance of this vast region. Regions that experience such interactions may become sites of intense activity, fostering conditions favorable for star formation. Understanding the effects of these solitary entities allows astronomers to glean insights into the evolution of galaxies. Their solitary pathways reveal the complex interplay between stellar life cycles and the medium that envelops them, painting a clearer picture of the cosmos's intricate structure. The possibility of rogue stars interacting with planetary systems presents a profound area of exploration. These celestial wanderers, often ejected from their original clusters, traverse vast distances through the galactic halo, Encounters with star systems can result in gravitational perturbations, which may influence the orbits of nearby planets. Such interactions could lead to the ejection of these planets from their stable orbits, creating a dynamic environment where some bodies gain a solitary existence akin to their stellar counterparts. This phenomenon raises questions about the potential for rogue planets without a parent star. These celestial entities may drift in the darkness, yet still possess the ingredients for life. The subsurface oceans of icy worlds, warmed by radioactive decay, provide a plausible habitat for extremophiles. Observations have indicated that rogue stars may illuminate these wandering planets, allowing for transient moments of warmth and energy. Additionally, the gravitational influence of a rogue star could lead to the capture of other celestial bodies, forming transient planetary systems. The interactions may result in a rich diversity of orbits and conditions, fostering unique environments. Each rogue star, with its distinct history, contributes to the galactic narrative, weaving together the stories of both stars and planets that exist in the cold expanses of space. The discovery of hypervelocity stars has illuminated the dynamics of these solitary wanderers, originating from the gravitational influence of supermassive black holes. Such stars can achieve speeds exceeding 1 million kilometers per hour. This velocity allows them to escape the gravitational pull of their host galaxies, transforming them into intergalactic travelers. Observations reveal that hypervelocity stars are often ejected during stellar interactions, particularly in dense stellar environments. Once part of a binary system, one star may be propelled outward when its companion falls into the black hole, a process that speaks to the violent yet predictable nature of cosmic forces at play in this region. The tracking of these stars provides essential insights into the gravitational dynamics of black holes and the evolution of star systems. Their trajectories offer clues about the conditions that lead to such extreme velocities, reshaping understanding of stellar life cycles and interactions. In addition, these stars serve as markers, tracing paths through the interstellar medium, potentially influencing the formation and evolution of new stellar bodies. Their presence in distant regions of the universe demonstrates the vastness of cosmic environments, where even the most solitary entities contribute to the overarching structure of galactic halos. Each hypervelocity star carries with it the remnants of a complex history, shedding light on the interconnectedness of the cosmos. The intricate dynamics of black holes play a pivotal role in the formation of these rogue stars. When a massive star nears the event horizon of a supermassive black hole, gravitational forces can disrupt its orbit. This interaction often results in a gravitational slingshot effect, propelling one star at high velocity into the galactic halo. The ejected star, now traversing vast distances, carries with it the remnants of its celestial family. The process is not limited to supermassive black holes. Smaller, stellar mass black holes exhibit similar behavior. In dense star clusters, their gravitational influence can lead to the ejection of nearby stars. The interactions create a gravitational dance, where one star may gain the energy needed to escape while another loses momentum, becoming trapped in an orbit around the black hole. This delicate balance of forces shapes the evolution of stellar populations within these regions. Rogue stars, once ejected, become solitary travelers, journeying through the dark expanse of the galaxy. They contribute to the galactic ecology by enriching interstellar space with heavy elements produced during their lifetimes. This process fosters new star formation, weaving the fabric of the universe and ensuring its evolution continues. Even as these solitary wanderers drift through the cosmic void, the cycle of creation and destruction remains an essential aspect of the cosmic narrative. Rogue stars traverse the vastness of space, unbound by the gravitational embrace of their original galaxies. This freedom often leads them into encounters with other celestial bodies, resulting in interactions that shape galactic evolution. The phenomenon known as galactic cannibalism describes instances where larger galaxies consume smaller ones, a process that can eject rogue stars into the halo of the surviving galaxy. These solitary travelers, stripped from their parent systems, carry remnants of their origins and stories of destruction. The dynamics of such interactions reveal the intricate dance of gravity, where stellar remnants collide and merge, contributing to the growth of larger galactic structures. Within the galactic halo, rogue stars often exist in isolation, wandering through dark voids, remnants of once vibrant star systems. The movements of these stars are dictated by the gravitational pull of more massive entities, marking their trajectories with both randomness and purpose. Observations indicate that many rogue stars originate from interactions involving supermassive black holes, where intense gravitational forces lead to the ejection of stars at high velocities. This process not only alters the stellar population of galaxies, but also influences the distribution of dark matter within the cosmos. Each rogue star, with its unique history, serves as a silent witness to the relentless cycles that govern the universe, embodying the harsh realities of cosmic evolution. The theoretical models of rogue star dynamics illustrate the intricate pathways these celestial bodies traverse through the galactic halo. By examining the gravitational interactions that propel them away from their host galaxies, researchers can better understand the mechanisms behind their ejection. Close encounters with massive stars or black holes often initiate this process, imparting sufficient energy to liberate them from gravitational binds. The dynamics of these ejections reveal the complexities of star formation and evolution. Dense stellar environments, like star clusters, become breeding grounds for such interactions. The gravitational perturbations in these regions can lead to the formation of binary systems, which may eventually result in one star being expelled at high velocities, while its companion remains bound. Simulations of rogue star trajectories indicate that some may travel vast distances, wandering through intergalactic space for billions of years. These models suggest that rogue stars can interact with dark matter, influencing the distribution of this elusive component of the cosmos. Understanding their paths provides insights into the broader structure of the universe. The analysis of these solitary travelers contributes to the ongoing discourse on the fate of stars and the evolution of galaxies. Each rogue star represents a piece of the cosmic puzzle, shedding light on the processes governing stellar life cycles and the dynamic nature of the galaxy itself. The unique characteristics of rogue stars provide invaluable insights into the formation and evolution of galaxies. Their solitary journeys through the galactic halo reveal the gravitational influences that shape stellar paths. Such stars often emerge from dynamic interactions within dense stellar environments, indicating the turbulent history of their birthplace. The ejection mechanisms at play highlight the chaos that occurs during stellar collisions or the gravitational pull from nearby massive objects. Understanding these wanderers enhances knowledge of dark matter distribution as they traverse regions where conventional matter is scarce. Their trajectories serve as observational markers, allowing astrophysicists to infer the unseen forces that govern galactic structure. This exploration of rogue stars aids in piecing together the timeline of galactic evolution, from the primordial gas clouds to the intricate systems found today. Additionally, the chemical compositions of these stars can offer clues to the processes of nuclear synthesis occurring in various astrophysical environments. By analyzing their spectra, Researchers can trace the origins of elements and their dispersal throughout the universe. This knowledge deepens the comprehension of cosmic recycling and the interconnectedness of matter across vast distances. Rogue stars, in their isolation, thus contribute to a more nuanced understanding of the cosmos, emphasizing the intricate web of interactions that shape the universe's evolution. The cosmic microwave background, a relic from the dawn of the universe, serves as a backdrop to the journey of rogue stars. These solitary wanderers drift through the vast expanses of the galactic halo, often traversing regions filled with this ancient radiation. The remnants of the Big Bang provide a constant reminder of the universe's infancy, while rogue stars, formed from the remnants of stellar explosions, carry the legacy of their birth in their luminous cores. Interactions between rogue stars and the cosmic microwave background reveal much about the conditions of the early universe. The faint glow of the background radiation, permeating space, can be influenced by these stars, altering the local thermal environment. This effect helps scientists glean insights into the processes of star formation and the dynamics of galactic evolution over billions of years. The isolation of these stars does not equate to a lack of influence. Their passage through the universe can lead to the scattering of elements forged in their interiors, enriching the interstellar medium. This dispersal supports the cycle of matter, facilitating the formation of new stars, planets, and potentially life. Understanding these connections allows for a more profound appreciation of the cosmic narrative, where rogue stars act as both participants and observers in the ongoing story of creation and transformation. Stellar migration reveals a complex journey, marked by gravitational interactions and the passage through vast interstellar spaces. These solitary travelers traverse the galactic halo, often ejected from their original stellar clusters due to dynamic encounters with neighboring stars. This process results in trajectories that take them far from their birthplace, where they drift into regions devoid of the familiar gravitational embrace. The mechanics of this migration are intricate. As they move, these stars interact with the interstellar medium, subjecting themselves to forces that influence their velocity and direction. The characteristics of this medium, including density and temperature, play a crucial role in shaping their paths over vast timescales. The movements of rogue stars contribute to the redistribution of chemical elements throughout the galaxy, a phenomenon that is essential for the evolution of galactic structures. Upon their arrival in new territories, these stars may ignite further star formation, enriching the regions they inhabit. This interaction fosters environments where new celestial bodies can emerge. The remnants of older stars, including those that have undergone supernova explosions, mix with the materials brought by these wanderers, creating a mix of stellar debris that adds to the complexity of cosmic evolution. Rogue stars traverse the vastness of the galactic halo, their solitary journeys revealing aspects of cosmic evolution not easily observed. Often, they pass near dense clusters of matter, where gravitational lensing phenomena take place. This bending of light occurs due to the intense gravitational fields created by massive objects, distorting the appearance of background galaxies. The effect allows for the observation of distant celestial bodies that would otherwise remain hidden in the vast expanse. When rogue stars interact with such gravitational wells, they can further illuminate the characteristics of their surroundings. Light from more distant objects appears more pronounced, creating arcs and rings that serve as cosmic markers. This phenomenon not only enhances our understanding of space, but also provides insight into the distribution of dark matter, which remains enigmatic yet fundamental to the structure of the universe. The trajectories of these stars, often ejected from their birthplaces, contribute to the dynamic evolution of galaxies. As they drift through the halo, their paths can influence the formation and behavior of other celestial objects. Each rogue star carries a history, whispering tales of unique formation conditions and stellar life cycles. Their solitary existence embodies the complexities of cosmic interactions, emphasizing how even the loneliest travelers can shape the universe in profound ways. Cosmic rays, high-energy particles that permeate the universe, find a significant source in rogue stars. These solitary wanderers, untethered by gravitational bonds, experience tumultuous life cycles. When they undergo supernova explosions, they release immense amounts of energy into the surrounding void. This energy is pivotal in accelerating particles to speeds approaching that of light. The aftermath of such explosions contributes to the interstellar medium, enriching it with heavy elements and offering fertile ground for the formation of new cosmic rays. As particles collide with matter in this region, they can be further energized, creating a cascade of secondary particles. The interactions here are complex, with rogue stars serving as pivotal agents in the dynamic interplay of energy and matter. In regions where rogue stars congregate, the density of cosmic rays increases significantly, influencing the local astrophysical environment. These energetic particles can penetrate celestial bodies and influence atmospheric processes on planets, fostering a deeper understanding of cosmic radiation's effects on potential habitability. Research indicates that the contribution of rogue stars to cosmic ray production may be more substantial than previously acknowledged. Each solitary star's death, while individual in its occurrence, resonates through the cosmos, leaving an indelible mark on the very fabric of the universe, shaping the pathways of energy and matter across vast distances. The search for rogue stars stems from the need to understand these isolated celestial bodies and their roles in galactic evolution. Numerous astronomical surveys have been initiated to track their movements and characteristics. Ground-based observatories, equipped with advanced spectroscopic instruments, scan the night sky for faint signatures that indicate the presence of these elusive wanderers. Each observation contributes invaluable data regarding their velocities, luminosities, and compositions. Space missions have also played a pivotal role in this endeavor. Telescopes launched beyond Earth's atmosphere, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, provide unprecedented clarity, revealing details obscured by the atmosphere. These instruments probe deep into the galactic halo, identifying stars that have been ejected from their host galaxies due to gravitational interactions or supernova events. Cataloging these rogue stars allows astronomers to paint a clearer picture of stellar dynamics and the gravitational forces at play within clusters. The analysis of their trajectories yields insights into the history of galactic mergers and interactions. This knowledge helps refine models of galaxy formation and evolution, elucidating how solitary stars influence their surroundings over cosmic timescales. Each new discovery adds depth to our understanding of the universe, unveiling the paths taken by these wayward luminaries as they traverse the vast emptiness of space. Rogue stars inhabit a variety of galactic environments, each influencing their characteristics and behavior. In the outskirts of spiral galaxies, these stars often emerge from the gravitational interactions that occur during close encounters with stellar clusters or other massive celestial bodies. The collision of gravitational forces can propel a star away from its birthplace, allowing it to roam freely through the galactic halo, a region rich with dark matter and diffuse gas. When located in the vicinity of globular clusters, the dynamics shift significantly. The dense gravitational fields present, can facilitate the ejection of stars at high velocities, sending them on paths that lead into intergalactic space. These high-speed rogue stars carry vital information about the clusters from which they originate, further enriching our comprehension of stellar evolution in crowded environments. In contrast, within the remnants of galactic mergers, rogue stars can form from the chaotic aftermath. Here, stellar material is often redistributed, birthing new stars while ejecting others. These remnants wander through disrupted stellar fields, often årskallards tave misuain, offering insights into the processes that shape galaxies over billions of years. The study of rogue stars across diverse settings reveals the intricate connections that bind galactic evolution, highlighting their role as messengers of cosmic history. Each solitary traveler encapsulates the silent legacy of the stellar population from which it has broken free. The evolutionary pathways of rogue stars reveal a complex interplay of forces and processes. These stars often emerge from massive stellar clusters, where gravitational interactions can lead to ejections from their original formations. Over time, these solitary entities traverse vast distances, becoming witnesses to the cosmic tapestry that unfolds in their wake. Interactions with other celestial bodies, particularly during close encounters, can facilitate their ejection, propelling them into the depths of the galactic halo. The dynamics of these encounters highlight the intricacies of stellar evolution, emphasizing how the life cycle of a star can dramatically shift due to the gravitational influence of its neighbors. Once liberated, they may undergo significant transformations. These transformations might include changes in luminosity and spectral characteristics as they travel through different regions of the galaxy, impacting the interstellar medium they encounter. Their isolation can also lead to unique evolutionary trajectories, where they evolve independently of their former companions. The distribution of rogue stars across the galactic halo provides insight into the history of their host galaxies. Mapping their locations and velocities allows astronomers to infer the gravitational influences and interactions that shaped their journeys. Understanding these pathways not only enriches our knowledge of rogue stars, but also deepens comprehension of galactic evolution as a whole. The connection between rogue stars and gamma-ray bursts presents a fascinating intersection of stellar dynamics and high-energy astrophysics. Isolated from their birthplaces, these solitary entities can evolve under unique conditions, possibly leading to catastrophic outcomes. When a rogue star reaches the end of its life cycle, it may undergo core collapse, resulting in a supernova event. In specific scenarios, this event can ignite a gamma-ray burst, one of the most energetic phenomena in the universe. Observations suggest that the mechanism behind this transformation involves the intense gravitational forces exerted by the star's core as it collapses. As it collapses, it can emit jets of energy that travel at nearly the speed of light, producing gamma rays that outshine entire galaxies for brief periods. This region of space becomes illuminated in a flash, allowing astrophysicists to study these fleeting occurrences and their origins. These bursts, while rare, serve as vital markers in the cosmic landscape, offering clues about the conditions under which rogue stars exist. The study of their aftermath can reveal the elemental composition of the universe, as the energy released facilitates the creation of heavy elements. Understanding the relationship between rogue stars and gamma-ray bursts enhances the broader narrative of stellar life and death, illuminating the intricate web of cosmic events that shape galactic structures. Rogue stars play a pivotal role in the ongoing process of star formation within galaxies. Their solitary journeys through the vastness of the galactic halo can influence the interstellar medium, the dense gas and dust that serves as the building blocks for new stars. As these nomadic luminaries traverse different regions, they compress surrounding gas clouds through their gravitational forces. This compression triggers the conditions necessary for star formation, igniting new life in areas previously dormant. The interaction between rogue stars and dense molecular clouds can lead to the collapse of these nebulae, initiating a cycle of stellar birth. This phenomenon contributes to the dynamic evolution of galaxies, fostering a diverse array of stellar populations. In regions where these solitary wanderers drift, new stars ignite, enriching the chemical composition of the galaxy and ensuring the continuation of its life cycle. Additionally, the dispersal of materials from rogue stars, often resulting from supernovae, contributes to the formation of new stellar systems. The remnants of these explosions inject heavy elements into the interstellar medium, providing the necessary ingredients for the creation of planets and additional stars. This continuous interplay between solitude and creation illustrates the complex nature of cosmic evolution, emphasizing the importance of rogue stars in shaping the universe's structure and diversity. An intriguing aspect of rogue stars lies in their potential to host exoplanets. While the absence of a stable stellar environment raises questions about the viability of planetary systems, these stars, propelled through the galactic halo, may still harbor worlds of their own. The gravitational influence exerted by a rogue star can capture celestial bodies, drawing them into orbit despite the inherent instability. The conditions surrounding these planets, often classified as rogue planets themselves, can vary significantly from those within robust star systems, isolated from the warmth of a central sun. They may possess atmospheres sustained by geothermal activity or internal heat. Such environments could foster unique forms of chemistry and life, defying conventional expectations. The search for these exoplanets orbiting rogue stars expands the horizons of astrobiology. Understanding their formation mechanisms reveals the potential for diverse planetary characteristics, ranging from icy surfaces to volcanic landscapes. As these lone travelers navigate the vastness of space, the possibility of capturing fragments of matter and potential life becomes increasingly significant. Observational techniques, such as gravitational microlensing, offer methods to detect these elusive worlds. Each discovery adds to the mosaic of knowledge surrounding the cosmos, revealing the myriad ways in which celestial objects interact. The existence of exoplanets around rogue stars challenges existing paradigms, inviting further exploration into the nature of life beyond familiar stellar realms. Theoretical implications of rogue stars extend beyond mere astrophysical curiosity, reaching into the enigmatic realm of dark energy. This region of space, characterized by its accelerating expansion, presents a compelling backdrop for the study of these solitary wanderers. Their isolation allows for unique gravitational influences, which may offer insights into the nature of dark energy itself. Observations suggest that rogue stars could serve as distant markers, illuminating the gravitational effects caused by dark energy on cosmic structures. The gravitational pull exerted by these stars, albeit minimal, may contribute to the overall dynamics of galactic formations. This relationship implies that understanding the distribution and behavior of rogue stars could enhance comprehension of cosmic evolution. Research indicates that the presence of rogue stars might influence the dark energy equation of state. Variations in the density of these solitary entities could alter estimates of cosmic expansion rates, providing a clearer understanding of how dark energy interacts with visible matter. The study of rogue stars, therefore, becomes pivotal in refining theoretical models. Their unique existence in the vastness of the universe amplifies questions about the fundamental forces at play. Each rogue star represents not just a solitary entity drifting through the infinite, but a potential key to unlocking the mysteries of dark energy and the universe's ever-expanding nature. The wraith of ever-expanding nature, their presence within the galactic halo, disrupts the established gravitational balance of surrounding structures. This region, populated by gas clouds, dark matter, and remnants of ancient star formations becomes a dynamic arena where rogue stars exert influence. Their high velocities allow them to traverse vast distances, occasionally colliding with other stellar bodies or interstellar matter, leading to interactions that can trigger star formation or alter the trajectories of nearby objects. All such events contribute to the overall evolution of galaxies, demonstrating how these wandering stars play a role in the cosmic dance of matter. Observations indicate that rogue stars can introduce metallicity changes in their wake, enriching the interstellar medium as they shed material. This process enhances the potential for new generations of stars to form, thus impacting the life cycle of galaxies over time. Additionally, rogue stars serve as cosmic messengers, providing insights into the gravitational interactions that govern galactic mergers and collisions. Their paths, influenced by dark matter's elusive presence, reveal the unseen gravitational web connecting galaxies within their clusters. The study of these isolated wanderers sheds light on the fundamental forces that shape the universe. Their solitary journeys through the cosmos underscore a complex narrative of interaction and transformation, revealing the quieter yet consequential aspects of galactic dynamics. Stellar mass loss plays a pivotal role in the ejection of stars from their original systems. This phenomenon often occurs during the later stages of a star's life cycle, particularly in massive stars. As they exhaust their nuclear fuel, these celestial bodies undergo significant changes. The outer layers become unstable, leading to the shedding of mass in the form of stellar winds or dramatic supernova explosions. Such mass loss alters the gravitational binding within a star system. Reduced mass can weaken the gravitational pull on companion stars, allowing them to break free from their original orbits. The remnants of a massive star, now stripped of its outer layers, can drift through space, leaving a trail of gas and dust behind. This process contributes to a dynamic environment within the galaxy, where interactions between stars can lead to a cascade of ejections. Additionally, the presence of binary systems can further complicate these dynamics. When one star in a binary system goes supernova, the sudden mass loss can propel the second star into a new trajectory, often leading it to become a rogue star. These ejected stars traverse vast distances, often traveling through the halo of a galaxy, where they may contribute to the formation of new structures or interact with other celestial objects. The trajectories of rogue stars present intriguing possibilities for the future of galactic evolution. Current models suggest that as they journey through the halo, these solitary travelers may encounter remnants of dark matter and primordial gas. The interactions can lead to gravitational perturbations, potentially triggering the formation of new stellar clusters. Predictions indicate that rogue stars could play a significant role in the redistribution of mass within galactic halos. Their influence might alter the dynamics of neighboring stars and gas clouds, fostering environments ripe for new star formation. As they drift through these regions, their presence may catalyze the collapse of dense molecular clouds, resulting in the birth of new stellar bodies. Long-term simulations forecast that some rogue stars could eventually be captured by more massive galaxies, becoming part of their stellar population. This incorporation would enrich the chemical diversity of the galaxy, influencing subsequent generations of stars through processes such as supernova explosions and the distribution of heavy elements. The future of these wandering luminaries also raises questions about their eventual fate. Many are predicted to collide with other celestial bodies, while others may be ejected from their new homes, continuing their solitary journeys across the cosmos. Each event adds to the complex narrative of star formation and galactic dynamics, ensuring the ongoing evolution of the universe. Rogue stars, drifting through the vastness of space, often find themselves in proximity to stellar clusters. The gravitational influences at play within these clusters create a dynamic environment. Stars born in clusters typically remain bound by gravity, forming tight-knit systems. In contrast, rogue stars, ejected from their birthplaces, traverse the galaxy alone, yet their paths can intersect with these clusters. During these encounters, rogue stars may impart energy to the cluster's members. Their presence can disrupt established orbits, influencing the trajectories of neighboring stars. This interaction often leads to the exchange of mass and momentum, affecting the evolution of both the rogue individual and the cluster as a whole. The gravitational pull of a rogue star can trigger perturbations, leading to the formation of new stars or the destabilization of existing systems. Clusters, the collapses, in their turn, also play a role in shaping the fate of rogue stars. The dense environment can increase the likelihood of encounters with other celestial bodies, potentially leading to further ejections or capture. The interplay between these solitary travelers and their clustered counterparts highlights the intricate network of galactic dynamics. These interactions contribute to the ongoing story of stellar evolution, demonstrating that even in isolation, rogue stars are far from disconnected from the broader cosmic landscape. The galactic halo, an expansive and diffuse region surrounding the Milky Way, plays a pivotal role in the distribution of dark matter. Within this vast expanse, rogue stars traverse paths influenced by the underlying gravitational effects of this unseen mass. These solitary travelers, liberated from their original stellar clusters, carry with them vital clues about the halo's structure and composition. As they wander through the halo's depths, their trajectories become altered by the gravitational pull of dark matter. Observations suggest that the density of dark matter varies significantly throughout this region, creating a complex gravitational landscape that shapes the movement of these stars. The data collected from rogue stars allows astrophysicists to infer the distribution of dark matter, providing insight into its role in the formation and evolution of galaxies. Loneliest serves as a beacon, illuminating the invisible framework that underpins galactic dynamics. By studying their velocities and trajectories, researchers can map the dark matter halo with increasing precision. In this way, the rogue stars become essential components of the cosmic puzzle, linking the tangible universe to the elusive nature of dark matter. Their existence emphasizes the interconnectedness of celestial phenomena, reminding us that even the most solitary entities contribute to the understanding of the universe's deeper mysteries. Rogue stars play a significant role in the complex processes of galaxy formation. These wandering giants, untethered by the gravitational pull of their parent galaxies, can influence the dynamics of gas and dust in the interstellar medium. When they collide with other celestial objects or pass through dense regions of material, they can trigger the formation of new stars, creating ripples in the cosmic fabric that echo throughout their vicinity. The energy released during these interactions is substantial, often resulting in shock waves that compress surrounding gas clouds. This compression can lead to the birth of stars, contributing to the overall star formation rate within galaxies. This phenomenon is particularly pronounced in regions where rogue stars traverse densely populated stellar nurseries, injecting fresh energy into the surrounding environment. In addition, the mass loss from these solitary stars, through processes such as stellar winds or supernova explosions, enriches the surrounding medium with heavier elements. This material, often referred to as stellar ejecta, becomes part of the galactic ecosystem, aiding in the formation of new stars and planetary systems in the future. Rogue stars, while seemingly isolated, serve as catalysts for cosmic evolution, illustrating the delicate balance between solitude and interconnectedness in the universe's grand design. Their journey through the galaxy is a reminder of the intricate interplay of forces that shape the cosmos. Surveys of the local group reveal a fascinating distribution of rogue stars. These solitary travelers, ejected from their original systems, drift through the vastness with no stellar companions. Observations indicate that they are not merely rare anomalies, but rather a significant component of the galactic landscape. Their prevalence suggests a dynamic history of interactions among stars, particularly in densely populated regions. Spectroscopic analysis of these stars provides insight into their ages and compositions. Many exhibit characteristics of younger stellar populations, indicating that their ejection is often a product of gravitational encounters within star clusters. Such events can lead to a swift expulsion from a system, altering their trajectories and isolating them from the nurturing embrace of their birth environments. The movement of these stars is influenced by the gravitational pull of nearby galaxies. As they traverse the local group, they interact with the gravitational fields of large spiral galaxies, such as the Milky Way and Andromeda, further complicating their paths. These encounters can alter their velocities, sometimes propelling them into the intergalactic medium. Tracking the paths of these rogue stars enhances understanding of galactic evolution. Each solitary journey tells a story of cosmic dynamics, revealing the profound and often chaotic nature of stellar life beyond the confines of traditional systems. Their existence underscores ongoing processes that continue to shape the universe. The chemical enrichment of the universe relies significantly on the contributions made by rogue stars. These solitary travelers, often ejected from their original families, forge their own paths across the galactic halo. Within their cores, nuclear fusion generates essential elements, transforming lighter atomic structures into heavier ones. This process happens over millions of years. When rogue stars reach the end of their life cycles, they often explode as supernovae. This violent event disperses their core materials into the surrounding interstellar medium. The remnants enrich the cosmos, providing the building blocks for future generations of stars and planets. This cycle establishes a continuous flow of matter that nourishes the formation of new celestial bodies. As these elements mix with gas clouds, they facilitate the birth of stars, fostering the conditions necessary for life to emerge. Various studies indicate that the abundance of certain elements across different galactic regions traces back to the contributions of rogue stars. Their isolated journeys through the galaxy reveal a complex narrative of cosmic evolution. This enrichment process also highlights the interconnectedness of various stellar phenomena, illustrating how even the most solitary of entities plays a pivotal role in the broader cosmic ecosystem. The dynamics of rogue stars reveal intriguing interactions with the magnetic fields present in galaxies. As these stars drift through the galactic halo, they encounter regions of varying magnetic intensity, which can influence their trajectories and behavior. This magnetic interaction is not merely a passive phenomenon. It actively shapes the movement of these solitary travelers, guiding them through the vast emptiness surrounding them. These magnetic fields, generated by the collective motion of charged particles, serve as invisible highways, subtly altering the paths of rogue stars. The interplay between stellar motion and magnetic influence can lead to complex behaviors, including alterations in velocity and changes in luminosity. When a rogue star ventures close to a more massive body, such as a black hole or a dense cluster, the magnetic forces may amplify, creating an environment ripe for energetic events. The resulting phenomena can be observed in the emissions from these stars, often detectable across various wavelengths. High-energy radiation may emanate from interactions with the interstellar medium, demonstrating how these isolated entities continue to contribute to galactic processes. This relationship not only illustrates the importance of magnetic fields in shaping stellar life cycles, but also emphasizes the role of rogue stars in maintaining the dynamic equilibrium of their regions. These contributions extend far beyond their solitary existence, weaving them into the fabric of galactic evolution. The role of rogue stars in cosmic structure formation is significant. These solitary entities traverse vast interstellar distances, often dislodged from their original clusters. As they move through the galactic halo, they interact with the surrounding medium, influencing the distribution of dark matter and baryonic matter. This interaction can lead to localized gravitational effects, altering the trajectories of nearby gas and dust, which are essential components for star formation. In regions lacking sufficient density, rogue stars can ignite processes that trigger the collapse of gas clouds. This results in the formation of new stellar bodies, contributing to the complex life cycle of galaxies. The energy and momentum imparted by their passage can create shock waves, compressing materials and fostering conditions favorable for star birth. The absence of a stable gravitational anchor means that these stars carry unique chemical signatures, remnants of earlier nuclear synthesis processes. Their ejection from clusters does not erase their history. Rather, it disseminates their enriched materials across the galaxy. These contributions enhance the chemical diversity in regions that may otherwise remain barren. Rogue stars serve as vital agents in the cosmic landscape, facilitating the ongoing evolution of galaxies. Their journeys through the galactic halo provide crucial insights into the dynamics of star formation, revealing the intricate interplay between isolation and interaction in the universe. Rogue stars contribute significantly to the understanding of the Milky Way's evolution, originating from various stellar populations. These solitary travelers carry with them unique signatures of their birthplaces. Tracking their trajectories through the halo allows astronomers to reconstruct the history of star formation, migration, and interaction within the galaxy. The gravitational effects of these stars on surrounding matter can illuminate the processes that govern the movements of gas and dust in the vast expanse. Observations reveal that some rogue stars may have been ejected from their original clusters due to gravitational interactions with more massive companions, while others may have formed in isolation. This duality in their origins highlights the complexity of galactic evolution. The interactions of these stars with the interstellar medium can lead to the enrichment of heavier elements throughout the halo, thereby influencing the chemical composition of new generations of stars. In regions where rogue stars congregate, the potential for triggering new star formation becomes evident. Gas clouds may collapse under the influence of the rogue star's gravitational pull, fostering the creation of new stellar systems. This ongoing process illustrates the continual transformation of the Milky Way, shaped by the actions of both solitary stars and the larger structures that encompass them. Such insights solidify the understanding of the galaxy as a dynamic entity, forever evolving through a myriad of interactions. Interstellar medium interactions reveal the complex relationships between rogue stars and their environment. These solitary travelers traverse the vast expanses of the galactic halo, encountering clouds of gas and dust that define their paths. Each encounter can alter their trajectories, pushing them into new regions of space, where the density of matter varies greatly. The interstellar medium consists of hydrogen, helium, and trace amounts of heavier elements, forming a rich backdrop for these stars. When a rogue star moves through this medium, shocks and waves are created, leading to the compression of gas. This compression can trigger the formation of new stars in regions previously deemed inhospitable. These interactions also provide essential clues to the chemical evolution of galaxies. The expelled materials from rogue stars contribute to the enrichment of the interstellar medium, influencing the next generation of stellar formations. The mixing of elements serves as a reminder of the interconnectedness of celestial objects, even in isolation. Observations of rogue stars engage astronomers in a deeper understanding of galactic dynamics. The study of their movement and the resultant interactions allows for a clearer picture of the life cycles of stars and the ongoing processes shaping the universe. Each rogue star narrates a story of solitude and connection, embodying the intricate fabric of cosmic evolution. Rogue stars illuminate the vast expanses of the universe, influencing our understanding of interstellar travel and the Fermi paradox. Their existence raises pertinent questions about the likelihood of intelligent life beyond Earth. The solitary journeys of these celestial bodies suggest that, amidst the darkness, there may exist countless potential pathways for life to emerge, hidden from our current observational capabilities. In this region, the migration of rogue stars through the galactic halo can disrupt stellar systems, altering the gravitational dynamics and possibly affecting planetary formation. The wandering nature of these stars implies that habitable zones may not be as static as previously thought. They may briefly inhabit regions conducive to life, only to vanish into the void, taking potential ecosystems with them. Fermi paradox, which posits the apparent contradiction between the high probability of extraterrestrial life and the lack of contact with such civilizations, finds new dimensions in these observations. If rogue stars possess the ability to alter the evolutionary trajectory of planets, then the absence of identifiable civilizations may not indicate their non-existence, but rather their transient nature, shaped by the unpredictable movements of these lonesome wanderers. In contemplating the implications of rogue stars, it becomes evident that our universe is a dynamic expanse where the interplay of chance and circumstance dictates the emergence of life in ways yet to be fully understood. Rogue stars present a unique challenge for astrobiology, as their solitary journeys through the vastness of space create isolated environments that may harbor life. The absence of stable orbits around a central star raises questions about the potential for planets to develop and sustain complex ecosystems. In these cold, remote regions, the gravitational influence of a rogue star may capture celestial bodies, bringing them into close proximity, albeit briefly, before drifting apart once again. As conditions fluctuate, these planets could experience extreme temperature variations, affecting the availability of liquid water, an essential ingredient for life as we know it. The brief periods of stability, coupled with the transient nature of their surroundings, may give rise to unique adaptations among any potential organisms. Life in such isolated settings might evolve mechanisms to withstand harsh conditions or utilize alternative biochemical pathways. The search for signs of life in connection with rogue stars requires innovative approaches, as traditional methods used for detecting exoplanets orbiting stable stars may not apply. Space missions targeting regions where rogue stars influence planetary systems could reveal valuable insights into the resilience of life forms, adapting to the relentless uncertainty of their cosmic environment. These studies may illuminate pathways toward understanding life's resilience in the face of isolation, reflecting the intricate balance between chaos and opportunity in the universe. The influence of rogue stars on stellar evolution theories cannot be understated. Isolated from their parent galaxies, these wanderers traverse vast interstellar distances, challenging traditional notions of star formation and life cycle. Their unpredictable trajectories introduce complexities to existing models, prompting scientists to reconsider the gravitational interactions that govern stellar dynamics. Research indicates that the presence of rogue stars may alter the chemical enrichment of interstellar mediums. When a rogue star explodes as a supernova, the dispersal of heavy elements occurs far from their original stellar nurseries, providing a unique perspective on cosmic recycling. This process may enrich otherwise barren regions, fostering new star formation in isolated pockets of space. The interactions between rogue stars and their environments also raise questions about the mechanics of gravitational influence. Such stars may disrupt the orbits of nearby celestial bodies, influencing the formation of planetary systems as they pass through various regions. The gravitational disturbances could lead to the ejection of materials, altering the course of nearby stars. These phenomena highlight the role of rogue stars as agents of change within the galaxy. Their existence prompts ongoing inquiries into how stars evolve in isolation and the subsequent impact on galactic architecture. Understanding these outliers enhances knowledge of the broader cosmic landscape, indicating a more intricate relationship between stellar phenomena and the universe's evolution. Rogue stars emerge across various cosmic epochs, each contributing unique insights into the evolution of the universe. During the early phases, shortly after the Big Bang, massive stars formed rapidly, fueled by the dense primordial gas. These short-lived entities often ended their lives in supernovae, ejecting material into the surrounding environment. The remnants of these explosions facilitated the formation of rogue stars as stellar debris coalesced under gravitational influences. In the subsequent epoch, the galactic halo harbored an increasing population of these solitary travelers. As galaxies developed, interactions and mergers initiated dynamic exchanges within stellar constituents. These encounters sometimes dislodged stars from their birthplaces, casting them adrift into intergalactic space. The study of these rogue stars reveals the ways in which gravitational forces and cosmic events sculpt stellar paths. Throughout the later epochs, the behavior of rogue stars continued to evolve, influenced by the changing structure of the universe. The gradual expansion and the formation of large-scale structures impacted their distribution and characteristics. Some rogue stars exhibit signs of past interactions, while others reveal the isolation that defines their existence. Analyzing the composition and movement of these stars allows insights into the history and dynamics of the galaxies from which they originated, painting a richer picture of cosmic history. The presence of rogue stars significantly influences galaxy mergers, acting as both witnesses and participants in these monumental interactions. Their journey through the vastness of space often leads them into regions where galaxies collide, exposing them to the chaotic gravitational forces at play. This region becomes a crucible of transformation, where the merged entities can reshape their stellar populations and dynamics. During these mergers, rogue stars can be drawn into the gravitational well of a galaxy, altering its overall compositions. Such interactions may result in these stars being captured, their orbits subsequently influenced by the collective mass of their new surroundings. In some instances, these stars become part of the galactic core, contributing to the growth of supermassive black holes. The gravitational interactions also lead to the scattering of stars, resulting in new configurations and the dispersion of stellar material across vast distances. These events can trigger star formation in regions previously devoid of activity, infusing new life into the galactic ecosystem. While merging galaxies evolve, rogue stars serve as remnants of earlier cosmic epochs, their solitary paths revealing insights into the processes that govern stellar evolution. They bridge the past and present, providing a glimpse into the celestial mechanics that shape the universe's continuous evolution. Their presence within the galactic halo introduces both gravitational perturbations and potential disruptions to nearby stellar systems. Rogue stars, untethered by the gravitational embrace of their parent galaxies, can affect the orbits of neighboring celestial bodies. This influence can lead to an increase in stellar encounters, where stars pass closely enough to interact gravitationally, altering trajectories and potentially ejecting planets from their systems. The interaction between rogue stars and established systems often results in a cascade of effects. When a rogue star passes through a stellar neighborhood, it may destabilize the orbits of existing planets, pulling them into wider, more eccentric paths, or even leading to collisions. Such disturbances might spark the formation of new planetary bodies through gravitational agglomeration of debris, showcasing the dynamism within these regions. In cases where rogue stars approach closely, their radiation can influence the atmospheres of orbiting planets, possibly stripping away protective layers and affecting habitability. The gravitational waves produced during these stellar encounters can also carry information about the mass distribution and dynamics of both the rogue star and the surrounding environment. Dynamic simulations reveal that these interactions are not merely random occurrences. Instead, they are integral to understanding the larger evolutionary processes that govern galactic structure and the life cycles of stars. The quiet chaos wrought by rogue stars underscores their role as significant players in the cosmic narrative. Rogue stars traverse vast expanses within the cosmic web, disconnected from the gravitational pull of their parent galaxies. This region of space, often characterized by filaments and voids, serves as the backdrop for these solitary wanderers. The intergalactic medium, a tenuous gas that fills the voids, influences their paths, occasionally altering trajectories through gravitational interactions with dark matter structures. In their journey through the cosmic web, rogue stars can illuminate previously hidden aspects of galactic formation and evolution. Their presence indicates the complex interplay of forces that govern star formation within galaxies. While they may drift alone, these stars carry with them the history of their birthplaces, remnants of stellar nurseries that once fostered their existence. The isolation of rogue stars contributes to the broader understanding of galactic dynamics. Their interactions with other celestial bodies within the web can lead to the formation of new star clusters, or even the disruption of existing ones. This phenomenon allows astronomers to study the effects of gravitational influences and the role of dark matter in shaping stellar paths. In the grand scheme, rogue stars act as markers within the cosmic web, tracing the intricate threads that define the structure of the universe. Their journeys encapsulate the ongoing evolution of the cosmos, revealing a universe still in the process of shaping itself. Computational simulations serve as vital tools in understanding these solitary wanderers. They allow scientists to recreate the conditions under which rogue stars are formed and ejected from their original stellar clusters. By modeling various scenarios, researchers can analyze the gravitational interactions and dynamic processes that lead to a star's expulsion into the galactic halo. These simulations incorporate vast amounts of data, including stellar masses, velocities, and the complex gravitational fields of surrounding celestial bodies. Running simulations across a range of parameters provides insights into how often rogue stars are generated and the potential environments that foster their journeys. This region of study is rich with implications, as it deepens comprehension of both stellar evolution and the large-scale structure of the universe. Simulations also facilitate investigations into the aftermath of rogue stars as they traverse the cosmos. Tracking their paths reveals potential encounters with other celestial objects, shedding light on the fate of these solitary entities. Such studies enhance the understanding of the overall dynamics within galaxies and the role of these stars in the cosmic ecosystem. With each iteration and advancement in computational techniques, knowledge continues to expand. The intricate web of interactions between these stars and their environments unfolds, contributing to a more nuanced picture of the universe's ongoing narrative. Rogue stars drift through the vastness of space, unbound by the gravitational embrace of galaxies. Their origins, often trace back to violent events such as supernovae or gravitational interactions within dense star clusters. In this region, stellar dynamics become a crucial factor in understanding the behavior of these solitary travelers. Explosive phenomena, such as the death of massive stars, can disrupt the delicate balance of gravitational forces, propelling some stars into intergalactic isolation. The movement of these stars is dictated by their velocities and the gravitational influences of nearby celestial bodies. Many rogue stars exhibit high velocities, allowing them to traverse great distances across the cosmic landscape. Interactions with dark matter and other gravitational anomalies can further alter their trajectories, creating a complex picture of their overall dynamics. Observing these solitary entities provides valuable insights into the processes that govern stellar evolution and the life cycle of galaxies. Their paths illuminate the interconnectedness of cosmic events, revealing how individual stars can impact the galactic environment. The study of rogue stars continues to challenge conventional views of stellar formation and migration, highlighting the dynamic nature of the universe. This exploration underscores the importance of these isolated bodies in refining our comprehension of galactic mechanics and the broader cosmic tapestry. Observational challenges arise prominently when studying rogue stars. Their solitary paths often place them far from the brighter, dense clusters typical of stellar formations. This distance diminishes the probability of conventional detection methods. Spectroscopic techniques, which rely on light emitted or reflected from celestial bodies, become less effective in identifying these wanderers. Without the gravitational companionship of other stars, their luminosity can be weak and easily obscured by the vast cosmic dust that permeates this region. The lack of a stable environment complicates the understanding of their formation and evolution. Traditional models of stellar life cycles, which typically involve interactions within a system, must be re-evaluated when considering the solitary nature of rogue stars. Variability in their spectral signatures introduces another layer of complexity. Fluctuations in brightness may be mistaken for transient phenomena, leading to misinterpretations of their behavior. In addition, the vastness of the galactic halo presents logistical challenges for observational campaigns. The immense distances involved require highly sensitive instruments capable of discerning faint signals across expansive fields of view. This necessity stretches the limits of current technology and demands innovative approaches to data collection. Such hurdles encourage the development of advanced methodologies, including the utilization of all-sky surveys and dedicated observatories aimed at unveiling the secrets held by these elusive cosmic travelers. Future observatories are poised to play a pivotal role in the exploration of rogue stars. Equipped with cutting-edge technology, these facilities will enhance our ability to detect and analyze these solitary wanderers. Advanced sensors and high-resolution imaging systems will improve the identification of faint light signatures, enabling astronomers to discern the characteristics of rogue stars with unprecedented clarity. The design of such observatories incorporates innovations in adaptive optics, allowing for the compensation of atmospheric distortion. This advancement will significantly sharpen the view of distant celestial objects, revealing details previously obscured. In addition, multi-wavelength capabilities will permit simultaneous observations across the electromagnetic spectrum. This approach facilitates a comprehensive understanding of the physical processes governing the formation and evolution of rogue stars. Collaboration among various international institutions will further amplify the effectiveness of these observatories. Sharing data and findings will foster a collective knowledge base, enabling researchers to track the pathways of rogue stars across the vastness of space. Instruments targeting gravitational wave emissions will also be integrated into future observatories, capturing evidence of interactions between rogue stars and other celestial bodies. These developments promise to deepen insights into the life cycle of stars that have broken free from their galactic confines, shedding light on their contributions to the cosmic environment and the broader structure of the universe. The cultural ramifications of rogue stars extend beyond their astrophysical significance. Historically, these solitary entities have ignited the imagination of astronomers and philosophers alike. Their unpredictable trajectories challenge conventional notions of celestial stability, prompting a re-evaluation of the cosmos as a dynamic and evolving landscape. The exploration of these stars has inspired a wealth of artistic representations, ranging from literature to visual art, reflecting humanity's enduring curiosity about the universe. Scientific communities have embraced rogue stars as symbols of resilience and independence within the vastness of space. Their ability to traverse the galactic halo serves as a metaphor for exploration and discovery, resonating with the human spirit's desire to break free from limitations. This notion has permeated educational initiatives, encouraging young minds to engage with astronomy and fostering a sense of wonder about the universe. Cultural narratives also weave these stars into discussions surrounding identity and belonging. Their isolation prompts reflections on the nature of existence and the interconnectedness of celestial bodies. The concept of a rogue star has even found its way into popular media, framing the life of these stars as a journey through the cosmos, resonating with themes of nostalgia and longing. As research into rogue stars progresses, their influence on both scientific and cultural realms continues to evolve, enriching the collective understanding of humanity's place in the universe. The legacy of rogue stars in astrophysics research extends far beyond their solitary paths. They serve as critical markers for understanding the dynamics and evolution of galaxies. Observations indicate that these stars can originate from gravitational interactions within dense star clusters, or be ejected during supernova events. The mechanisms behind this ejection offer insights into the gravitational forces at play within these stellar environments. The study of rogue stars contributes to a deeper comprehension of stellar life cycles and the processes that govern galactic formation. Their presence in the galactic halo provides clues about the early phases of the universe. Information gleaned from these solitary travelers can reveal the history and structure of galaxies, as well as the distribution of dark matter. Rogue stars, often found in remote regions far from their birthplace, challenge existing models of stellar dynamics. Researchers utilize advanced telescopes and observational techniques to track their trajectories. This process helps refine calculations surrounding stellar mass and composition, enhancing the understanding of nuclear synthesis in the universe. In addition to their scientific implications, these stars encapsulate the transient nature of existence within the vast cosmos. The solitary journey of rogue stars underscores the interconnectedness of all celestial bodies, reminding humanity of the delicate balance that sustains life amidst the infinite expanse. Emerging theories surrounding rogue stars illuminate the vast, uncharted territories of astrophysics. Current models suggest that these solitary entities may play a critical role in galactic evolution, contributing to the dynamics of dark matter and the structure of the universe. Investigations aim to determine how rogue stars influence their surroundings, potentially triggering star formation in the dense regions of the galactic halo. Observations utilizing advanced telescopes are revealing unexpected patterns in the distribution of these stars. It appears that some may originate from the gravitational interactions of massive black holes, which can eject stars into interstellar space at high velocities. This phenomenon invites deeper exploration into the mechanics of stellar dynamics and the fate of stars under extreme gravitational forces. The quest for understanding rogue stars also encompasses their chemical composition. Studies indicate that these stars may possess unique metallic content, providing insights into the early universe. This information could reshape theories regarding nucleosynthesis and the evolution of galaxies over billions of years. Analytical methods are evolving, with simulations increasingly mimicking the conditions of the early cosmos. These simulations illuminate the potential for rogue stars to carry information about the primordial state of the universe, guiding researchers toward new revelations in cosmology. As research progresses, the mysteries of these cosmic nomads will undoubtedly enhance our understanding of the universe's intricate web. Rogue stars serve as silent witnesses to the dynamic history of the cosmos. Detached from their parent galaxies, these stellar wanderers traverse vast expanses, providing invaluable insights into the evolution of cosmic structures. Their trajectories often span billions of years, creating a unique perspective on the intricate dance of gravitational interactions that shape galactic formation and dissolution. The presence of rogue stars hints at the complex gravitational influences in stellar nurseries and the eventual fate of star clusters. They embody the remnants of past galactic events, such as violent encounters or gravitational disruptions that led to their expulsion. This solitary existence contributes to the broader understanding of timescales within the universe, illustrating how individual entities can impact cosmic history over immense periods. Rogue stars also contribute to the chemical enrichment of interstellar space. As they age and eventually die, they release elements forged in their cores, seeding the surrounding regions with the building blocks of future stars and planets. Their life cycles, while isolated, create ripples that influence the evolution of nearby cosmic environments. In examining these wanderers, astronomers glean insights into the distribution of mass across the universe and the mechanisms that govern stellar migration. Each rogue star encapsulates a story of cosmic evolution, enriching our understanding of time itself within the vast expanse of the universe. Stellar population synthesis involves the study of how stars form, evolve, and appearance. Observations indicate that these solitary entities can carry with them unique chemical signatures. The elemental compositions found in rogue stars often differ from those in more stable star populations. This variance hints at the diverse environments from which they originated, including regions that may be more chaotic or undergoing rapid star formation. Some rogue stars originate from interactions within crowded star clusters. As these clusters evolve, gravitational forces can disrupt their members, expelling some into the vastness of space. The study of these ejected stars aids in reconstructing the history of star clusters, providing a clearer picture of the mechanisms behind star formation across the galaxy. Understanding the role of rogue stars in stellar population synthesis helps astronomers refine models of galactic evolution, revealing the complex interplay of forces that shape the cosmos over billions of years. Observations across multiple wavelengths are essential in unraveling the mysteries associated with rogue stars. These solitary travelers emit light in various segments of the electromagnetic spectrum, each providing unique insights into their composition and dynamics. Radio waves reveal the presence of magnetic fields, while infrared observations can uncover dust-enshrouded stars, offering clues about their formation environments. X-ray emissions indicate high-energy interactions, often arising from encounters with interstellar material or other celestial bodies. This data contributes to a comprehensive understanding of how rogue stars evolve after their ejection from clusters. Ultraviolet light serves as a marker for younger stars, illuminating the processes that lead to their expulsion from galactic neighborhoods. The integration of data from these diverse wavelengths enables a multifaceted analysis of rogue stars, allowing researchers to track their trajectories and determine their origins. This approach not only enhances the understanding of individual stars, but also sheds light on the vast networks of gravitational influence that dictate their paths. The behavior of these entities in different environments adds complexity to the models of galactic structure and movement. Examining the connections between rogue stars and their surrounding medium reveals the significance of stellar feedback in shaping the interstellar landscape. Such insights reveal a profound connection between rogue stars and the broader cosmological parameters that govern the universe. These solitary wanderers, ejected from their host galaxies, offer a unique perspective on the dynamics of galactic evolution. Their trajectories provide clues about gravitational interactions, star formation rates, and the distribution of dark matter across cosmic structures. The role of rogue stars in the galactic halo serves as a key indicator of these parameters. The abundance of such stars can illuminate the history of galactic mergers and the complex gravitational dances that shape stellar populations. Observations indicate that these stars often originate from massive star clusters, which, when disrupted, lead to the expulsion of individuals into the vastness of space. Studying the velocity distributions of rogue stars contributes to understanding the mass and shape of dark matter halos surrounding galaxies. Variations in their speed can reflect the gravitational influences of unseen mass, providing indirect measurements of cosmic density. This region of solitary stars also raises questions about the fate of stellar remnants and their contribution to cosmic enrichment. Elements produced in supernova explosions find their way into interstellar space, influencing the chemical evolution of future generations of stars. Surveys. In this quiet expanse, rogue stars drift silently, unveiling the intricate connections between individual celestial bodies and the grand structure of the universe. The influence of rogue stars extends beyond their solitary paths, impacting the chemical evolution of galaxies. These isolated entities, stripped from their original clusters, carry with them the remnants of nucleosynthesis processes that occurred during their formation. As they traverse vast regions of the galactic halo, they disrupt the prevailing chemical composition of the interstellar medium. When a rogue star reaches the end of its life cycle, it undergoes a supernova explosion, releasing an array of elements into the surrounding space. This event enriches the galactic environment with heavy metals, which are vital for the formation of subsequent generations of stars and planetary systems. The introduction of these elements fosters diverse chemical pathways, leading to complex molecules that can. Interactions with surrounding gas clouds also play a crucial role. The shockwaves generated by these explosions can compress nearby gas, inducing star formation in regions that may have otherwise remained dormant. This chain reaction illustrates the interconnectedness of rogue stars with their galactic surroundings, revealing a dynamic and evolving ecosystem. In regions where these stars are prevalent, the chemical landscape becomes increasingly complex. Over time, they facilitate a cycle of birth, death, and rebirth that shapes the very fabric of galaxies. Their existence serves as a reminder of how even the most isolated travelers can leave lasting imprints on the cosmos. Rogue stars occupy a unique position in the vast expanse of extragalactic astronomy. Observations reveal that these solitary entities can drift beyond the gravitational influences of their parent galaxies, often entering the intergalactic medium. This region, characterized by low density and high temperatures, provides a stark contrast to the bustling environments of galactic cores. Studies indicate that rogue stars can originate from various scenarios, including gravitational interactions during galaxy mergers or the violent ejection from stellar clusters. Such processes generate intriguing dynamics, leading to the dispersal of matter across vast distances. This dispersion enriches the intergalactic medium, contributing to the cosmic chemical evolution. The trajectories of these stars, unbounded by galactic confines, also hold importance for understanding cosmic structures. They can illuminate the invisible dark matter that shapes the very fabric of the universe. By tracing their paths and studying their properties, scientists gather valuable data that inform theories regarding galaxy formation and evolution. In the growing field of extragalactic astronomy, technological advancements enable more precise measurements of rogue stars. Techniques such as gravitational lensing offer insights into their mass and velocity, enhancing comprehension of their role in the cosmic landscape. The study of these wanderers continues to deepen understanding of the universe's intricate workings. These solitary travelers evoke profound reflections on existence and belonging within the cosmos. The absence of a gravitational anchor raises questions about the nature of destiny and the forces that guide celestial bodies. Each rogue star represents a journey unbound by the familiar structures of galactic life, highlighting the transient nature of stability in the universe. Their paths, often shaped by gravitational encounters or catastrophic events, suggest a reality where chaos and order coexist. This interplay prompts consideration of free will versus determinism, as even stars appear subject to the whims of their surroundings. The isolation of rogue stars can also be seen as a metaphor for the human experience, reflecting feelings of solitude in an expansive universe. The discovery of these stars within the galactic halo introduces complexities regarding the formation and evolution of galaxies. Their existence challenges traditional models of stellar evolution and formation, suggesting a more dynamic and interconnected cosmos than previously understood. This region of space, filled with these errant luminaries, invites exploration of the interconnectedness of cosmic entities. Each rogue star, while a singular entity, contributes to the broader narrative of cosmic evolution, influencing the matter and energy distributions over billions of years. The philosophical implications of their existence continue to inspire inquiry into the fundamental nature of reality and our place within it. The significance of these solitary travelers in galactic studies is profound. Rogue stars provide a unique lens through which to examine the dynamics of galactic evolution and structure. Their trajectories offer insights into the gravitational interactions that govern stellar formation and the dispersal of matter throughout the cosmos. Each rogue star serves as a remnant of gravitational encounters, possibly shedding light on past galactic mergers and the violent histories that shape galaxies. Data collected from these stars enrich our understanding of the galactic halo, a region that contains dark matter and influences the motion of visible matter. The study of rogue stars reveals the interplay between ordinary and dark matter, highlighting the complexities of cosmic architecture. Their presence challenges existing models and prompts the development of more sophisticated simulations to account for the intricate dance of celestial bodies within the vast expanse. Investigations into the chemical compositions of rogue stars also inform theories regarding the formation of galaxies and the evolution of stellar populations. By analyzing the isotopic signatures of these isolated entities, researchers uncovered details of nuclear synthesis events that occurred in the early universe. This understanding